Okay, hello everyone. Welcome to Aspen Plus tutorial videos. In today's video, I would like to talk about gas compressor. So for today, I would like to evaluate or investigate what would be the effect of feed gas pressure on the power requirement of our compressor, as well as evaluate what would be the capital cost when we want to set up our compression system. So in Aspen Plus, what I will do is I'm going to use a compressor block as well as use the economic evaluation features in Aspen Plus to see how the capital cost and install cost would differ when we change the feed gas pressure. So let's begin. Well, if you ask me, compressor in Aspen Plus is among the simplest unit operation that you can find in the software. So what you need to do is just select the unit operation, okay, put it in the flow sheet, connect your feed, and then or maybe connect your input and then connect your output or outlet stream, and then in the block itself, you need to specify your either pressure outlet or maybe compression ratio or pressure ratio or maybe pressure increase depending on the information that you have. And then you click simulate and then you click run, and Aspen Plus should not have any issues converging the result. And 99% of the time you should not have any issues, okay, to obtain the result. Well, even though modeling or simulating compression process in Aspen Plus is pretty straightforward, what I observe from my students, especially in the integrated design courses or maybe in plant design courses, what I observed was the student fail to see whether the result that they obtain make some kind of physical sense or not. So especially when it comes to temperature increase. We all know that compressor is basically a unit operation that would enable you to compress a gas by reducing its volume. And we all know that when we compress a gas, temperature also will increase because assuming we have a gas and then the gas undergoes, for example, an isentropic compression where the compression process occurs without any heat loss to the surrounding. So the gas, basically your system, will be compressed. And in this case, when you compress, we basically add work to the system. When we add work to the system, internal energy of your system would increase, and because internal energy of your system increase, obviously temperature will increase also. So we all know that, and I don't want to go into details into things like fundamentals of compressor, different types of compressors, or maybe multi-stage or single stage compressor, is which one is more efficient, or and things like that, because this video is not about that. But the only thing that I want to highlight here is, even though Aspen Plus will give you will converge or will give you a result, it doesn't mean that the result that you get makes some kind of physical sense, especially in terms of temperatures. What I observed was the student I know that when they run the simulation, they got the result, so they are happy. But when I check the temperatures, sometimes I see the outlet temperatures goes to 1,000 degrees Celsius, 1,400 degrees Celsius, 700 degrees Celsius, things like that, which does not make any physical sense, even though a mass balance and energy balance checks out. And this is where students should think, okay, whether temperature itself, the outlet temperatures, does it make physical sense or not? Because we are running a compressors, not reactor, not furnace, things like that. And compressor, they have a o-ring made out of polymers. They are running 24/7, and then they also have this lubrication oil. And then if you think the temperatures, if the outlet temperatures is in the range of 1,000, right, do you think it makes sense to run that? And we all know that if you refer to the textbook, or maybe if you even refer to this your supplier specification, they always say that the temperature of the outlet, oftentimes it should be less. The requirement should be less than 200 degrees Celsius. You can go ahead and check on the internet, or maybe textbook related to compressors, they should mention things like this. But I don't want to I don't want to yap a lot or ramble a lot about this, because this is not the main point of this videos anyway. First, I want to discuss what are the important equations that Aspen Plus use, okay, to evaluate some of the important metrics or properties when it comes to compressors. And if you run your compressors and then when you go to block and then choose simulation result, these are based, if you see this figure, typical simulation result on your bottom right here, these are the important, I would say, important properties or result that Aspen Plus would calculate. For example, here, brake horsepower, indicated horsepower, power loss, efficiency, mechanical efficiency, and so on and so on. So, well, to those who just want to run and then get the result, yes, this is the result. But for as an introduction, I would like to highlight what the important equation that would give you all of this information. So if you see this equation, so when a gas, okay, goes into the compressor, and then we want to compress from pressure 1 into pressure 2, okay, Aspen Plus would calculate the head to required to compress the gas from one pressure to higher pressure. In this case, indicated by P1 and then P2. So basically, they just need to integrate P1. They just need to integrate VdP, P1 over P2. This is not a thermal class. I have no idea. I don't know. I don't want to go into detail about how to solve this. But basically, all you need to do is just integrate this. You will get a head. Now, the relationship between P and V is basically P, V to the power of N equals to C, where C is constant and N is a polytropic exponent. For isothermal compression, the N value here is equal to 1. For isentropic compression, where there is no heat loss to the surrounding, N is equal to K, where K is basically a ratio of heat capacity. If we're talking about isentropic compression, you just need to integrate by applying PV to the power of K, where K is equal to C, where K is a CP over CV. There are also an equation to discuss when we talk about positive displacement compression, but we're not going to discuss it here. So yeah, I know it is a lot of information to be processed here, but the point that I want to highlight is Aspen Plus will calculate head by integrating, okay, this VdP equation from P1 to P2, and then they will also, when they integrate this, they will take into account what type of compression that you have, either isothermal or isentropic compression, polytropic compression, or even positive displacement compression. And by taking this into account, they will integrate and get the result. And that's pretty much it. So if you see here, okay, after you apply the I would say constraint or maybe associate or relevant equation associated to a certain type of compression, you will get the final equation for the head calculation. For example, here, I think this one, the one on the top, belongs to the equation for to calculate head for isentropic compression. Below here is polytropic compressions, where you have this weird and ugly equation, if you ask me. Now, you may ask how the efficiency, if you see in this simulation result, how the efficiency comes about. Now, efficiency comes about by dividing head with efficiency, and then you will get this delta H is basically a change of enthalpy. Now, this head, okay, the calculation for head is for a perfect gas, but we all know that none of the gases are perfect. That's why we input efficiencies. Now you have to understand efficiencies need to be input by yourself. So this information checks out. We already discussed this. This is how efficiency is reported in Aspen Plus. This number one. Okay, number two, how do we get indicated horsepower, which is HP, or this particular, I'll say, column and row? indicated horsepower. Indicated horsepower is just a change of enthalpy calculated from the previous slide, multiplied with the molar flow rate of the gas. And then how about brake horsepower? Brake horsepower is basically a total work. Brake horsepower can be obtained by dividing indicated horsepower with mechanical efficiency, which you need to input this one as well. This is optional. I often don't put it, but in this case, I input 80%, okay, mechanical efficiency. So when you divide, you will get brake horsepower required to compress a certain gas. Now, we also have a power loss. Power loss is just, brake horsepower minus indicated horsepower. This is how you get it. And lastly, network required for the compression system is just a summation of brake horsepower and work stream. Now, if you remember, in Aspen Plus, we have a work stream. If you decided to put a work stream, then Aspen Plus will take into account, okay, the work provided to the system and calculate network. But if you ask me, the most important part here, it would be your brake horsepower, because the rest network required, normally they will be the same, because I don't think we're gonna add a work stream in our simulation. And that's pretty much it. Outlet pressure, outlet temperatures, and asymptotic outlet temperatures is calculated based on the equations. Okay, I think there's enough introduction and background to our compression system in Aspen Plus. So today, as you can see in these slides, okay, these are the problem or process that we will model in Aspen Plus today. And for your information, all of these are extracted from this journal, Capital Cost of Compressor for Conceptual Design by William L. Lubin. From Lehigh Universities, published I think in 2018. I think you can. It is a very interesting journal. I recommend you to download and read it, because his finding is something new to me. Which the reason why I decided to use this as an example. What else? Yeah. Okay, before we begin our simulation, I just want to talk about the problem that the author here want to highlight or want to solve. So basically, according to the author, when we want to design a process, right, it is very important when we are at the conceptual stage. It is very important for us to have an accurate or reliable estimate of the costs associated with all of the unit operation. And according to the author, there are a lot of resources that are reliable and also easy to use, that can be utilized by the designer to provide an accurate estimation of the cost of the unit operation. It can be either in the form of graph, correlation, table, and whatnot. And also, according to the author, the capital cost estimation for pressure vessel and heat exchangers, as well as distillation column, depending on whether you get it from a different, depending on whether you use different resources or whether you use different correlation, all of the capital cost estimation are in good agreement. So basically, regardless of the correlation that you use or resource that you use, you will get to the same. I'm not saying exact, but you can get to the same, I would say, estimated values. However, according to the author, compressors are different. Okay, uh, number one, there are many correlation, according to the author, that you can use to calculate or to estimate the compressor cost. For example, here, if you see, I highlighted in maroon here, we have a Douglas correlation, Turton correlation, Peters correlation, CD the correlation, Ulrich, Calado, as well as Aspen Plus. Now, if you use all of this correlation and apply it to the same compressor that operate that operate similarly and run and compress the same gas, same temperature and same condition, you will get a drastically different capital cost. So the author used a case where the compressor, okay, compress 1000 kilomole per hour of nitrogen at 1 bar and 50 degrees Celsius. Basically, you want to compress with a compression ratio of 2.5. So based on his Aspen Plus result, the required brake horsepower is 10 kilowatts, which we will try to confirm later. So based on this brake horsepowers, the author applied all of this correlation, and he found out that the compressor costs are just different. Okay, it's not like like different. It's not like it is different, but it is the same range. But they are very different, drastically different. So to give you an idea, if you see here, these. I don't really, I cannot see because my videos is in front of this sentence, but I think this should be a Calados correlation. So if you see Calados correlation, they have a two equation where they have a compressor cost, which is this, motor cost, which is this equation. Douglas correlation is basically this equation, 8480 multiplied with the brake horsepower in kilowatt to the power of 0.82. Now, if we have, based on the case that the author used, okay, he used 10 kilowatt and put it in this in this equation. And he used the same brake horsepower for all of this method, and he found out that the capital costs are just way too different. And one thing for you to note is this equation are just depend on the brake horsepower. According to him, okay, this is just not enough. How about the effect of feed gas pressure, which is the variables that the author want to investigate? Because this cost depend on the power requirement only. So obviously we don't have, if we use all of this correlation, obviously you don't have to know about other operating conditions such as feed gas and type of gas and things like that. And this equation also, according to the author, they do not consider the suction gas pressure. And one thing the author also highlight here is Aspen Plus give higher compression costs, the highest actually, which is 2.5 million, which is good if you are dealing, if you want to have a very conservative estimate of the compressor cost. But the point here is all of these are just way too different, and the author want to investigate this. For Aspen Plus, we will try to confirm this number later on. So coming back to our design problem, what we need to do today is we will try to compress nitrogen gas at 50 degrees Celsius and 1 bar pressure inside the compressor, okay, to pressure of 2.5 bar, which correspond to the compression ratio of 2.5. And we will determine the power requirement for the compression. So according to the author, he get 10 kilowatt, and we will try to confirm. And also we will also try to find out whether is there a difference in terms of the power requirement when we vary suction gas pressure from 0.5 bar to 4.0 bar. And we will also generate a curve or graph that describe the relationship between suction gas pressure and capital cost requirement. In this case, these are the similar, it's the same compressor, but they use a different correlation. For Aspen Plus, it's around 2.5. I'm sorry, this is 2.5 millions, by the way, not this. I don't know. This is like what, 2.5 billions, or maybe 25 billion. This is wrong, by the way. It is 2.5 billions, and we will try to confirm these numbers. Other constraint, we will use ASME or ASTM, polytropic efficiencies of 80%, Robinson equation of state, and temperature of the outlet should be less than 200 degrees Celsius, recommended by Wallace et al., which is basically a textbook. So yeah, let's begin. So yeah, I have my Aspen Plus ready here. What I'm gonna do is I'm just gonna input our feed, our gas, which is nitrogen, only nitrogen. So just type nitrogens. I'm gonna hit next. So we know we're gonna use a Peng-Robinson equation of states. Nothing new here. Just hit next, and then wait for a second, and then go to the simulation environment. I'm going to close this first. So I'm going to choose pressure changes. Choose compressor, put it here. I'm gonna name my compressor as COMPRS maybe. So that's my compressor. I'm going to add my material stream, which I'm going to name as LP nitrogen, I guess. And then this one, outlet stream, I'm going to put down HPN2 for high pressure nitrogen. Escape, maybe I zoom in to allow you to clearly see or how my flow sheet looks like. And this is how it looks like. And then just hit next. Okay, our nitrogen enters at 50 degrees Celsius, 1 bar, and 1000 kilomole per hour. Very easy, nothing new here. Hit next. And this is the compressor input specification. So you can choose isentropic, polytropic, whatever. But in this case, I'm going to use polytropic using ASME method. If you ask me, by the way, if you refer to the textbook, they never use. I mean, number one, isothermal compression is not here because it's not even make sense to have isothermal compressor because it's just not going to work in real life. The ideal case would be isentropic, but in most cases, people usually use a polytropic compression because they are more closely resembling the real life compression system. In this case, after I choose a polytropic, and then you can choose a pressure ratio, which is 2.5. You can also choose a discharge pressure, 2.5. Either way is fine. In this case, the efficiency for polytropic is 80%. I'm not going to write down the mechanical efficiencies because it is not, number one, it is optional. Number two, the author does not include the mechanical efficiency values. So I'm just going to keep it empty. And when it comes to providing input for these efficiencies, if you refer to your textbook or journals and things like that, they always use polytropic efficiencies. There is around 80 to 85%. Okay. Just go ahead and then refer to these values on internet. It's either between 80 to 85. So this is the normal values that people would choose that closely resemble the efficiencies of your real compressor. And then you hit next, hit OK. Nothing new here. It is a compressor. As I said, it's a very simple process. I'm not going to bother to check my inlet and outlet mass balance because it is a physical process. So obviously mass is conserved. Temperature will rise, but it's okay. I don't have to check the process stream, but I can check the compressor from the compressor block itself. So I double click. I go to the result. So if you see, let me make it bigger. So these are polytropic based on what you choose. So brake horsepower is 1010.83, which is similar to the author's power requirement. If you remember author's power requirement, it is, as you can see, the power requirement by the author reported by the author is 1010 kilowatt. So that checks out. The next thing that I'm gonna calculate here is I'm gonna estimate using Aspen Plus whether the capital cost of running the compressor, whether it is around 2.5 million or not. So yeah, coming back to our compressor result. So temperature is less than 200, so that checks out. So nothing wrong over there. Efficiency is 80%, depend on us. Mechanical efficiency is just 100% because we don't specify, so it's okay. And I'm gonna close this. And what I'm gonna do next is I'm gonna click the economics tab here. I'm gonna activate the economics features. Let's wait for it to load. Okay, for you to activate the economics, you must make sure that your process is converged. It will give you a result, or else this economic button they will be activated, but first they will ask you to rerun the simulation so that simulation converge. So if you see here, the costing is activated, so no issues. What I'm gonna do next, I'm not gonna change all of these economics option, things like that, because this is not really about economic analysis. This is about compressors, and I don't want to waste time to explain about that. Maybe later, maybe that's worth for later discussion in different videos. But first, I'm gonna map my compressor. Map is basically a process where you assign, okay, a specific unit operation for the unit, the actual unit operation for your unit operation in Aspen Plus. Yeah, I'm not gonna change anything. Maybe I'm gonna evaluate options. Hit OK. I'm gonna use a default mapping, by the way. So as you can see here, the compressor is mapped to this centrifugal pump. Actually, you can change the type of compressor. You can change the mapping of your compressor by your own, but I'm not going to bother to do that. So I'm just going to cancel and hit OK. So if you see here, mapping is okay, sizing is checks out, evaluation also checks out. And if you see here, it is already evaluated. Now, if I go down, go to result summary, let's see, go to equipment. And if you see equipment cost or install cost is 2.580800 a million. And let's check whether these are the same or not with the author's result. So what author give is 2.58 million. So what I have is 2.58 million plus $300. So that checks out as well. So yeah, coming back to our Aspen Plus, this total install cost checks out. So I have no issues with the author's report. So I'm going to close. So what I'm going to do next is I'm going to vary the feed gas pressure and check whether the power requirement is similar, is changing or not. Because if the power requirement is changing, obviously the capital cost will change as well. That's number one. Number two, okay, after I change after I evaluate, okay, the power requirement for the compressor for different between 0.5 bar to 4 bar, I will also evaluate what are the capital cost requirement in Aspen Plus. So yeah, let's go back to our slides. As you can see here, when I try to vary the suction pressure from 0.5 to 4 bar, if you see this green curve, it is constant. Okay, it is constant around 10 kilowatt. So what does it mean here? 10 kilowatt on the secondary axis on your right or on my right. Suction pressure does not really change anything does not affect, okay, the power requirement at all. Okay, that's number one. Number two, if you see here, the blue curve here is the Aspen Plus simulation result by me. Okay, and the red curve here is the data from Lubin et al., which is the author, also generated using Aspen Plus. And basically, what I get and what he get are more or less the same. So his answer and my answer checks out as well. And for your information, this blue curve and red curve are on your the axis is on the primary axis, which is on your left side. Now you may ask why the compressor cost significantly decrease with suction pressure. If you remember, if you are using Douglas correlation or certain correlation, they are all a function of power requirement, horsepower, right? If you use the correlation, and if you see here that we have a constant power requirement, meaning that regardless of the feed suction pressure, this the correlation will give you a constant capital cost. But in Aspen Plus, as rightly proven by me and Lewin et al., as suction pressure increases, the install cost or your compressor cost decreases, which are totally the opposite of it's totally the opposite, I would say, observation compared when we use a correlation. Now, the question that the author, I would say, pose is why this thing happened. So according to the author, again, according to the author, compressor is a volumetric equipment. What does it mean here is if we want to compress a same mass, a same gas with a similar mass flow rate, okay, the gas with lower feed gas pressure, okay, to compress the same amount of gas, for a lower feed gas pressure requires a much larger, I would say, piston compared when you have a feed gas at higher pressure. So larger pistons mean bigger compressor. So when bigger compressor means bigger cost. That's the author's explanation, which I agree. And as I said here, to process a similar mass of gas, let's say 1 kmol per hour, right? Larger compressor is required for low feed gas pressure because low feed gas pressure contains less mass. So lower pressure means volume gas larger, so your piston is larger, compressor is larger, so capital cost larger. So that's the reason why, okay, the compressor cost decreases when you increase the suction pressure. And these are another example. So if I said, as I said before, if I use a Douglas equation shown in this black curve here, and it corresponds to the cost, installed cost in the primary axis on your left, they are constant. The reason why they are constant is because the power requirement is constant. That's it. Now, if we see the Aspen simulation by me, so it decreases. So let's say you want to use Douglas equation, you have to introduce a correction factors, which I have introduced here, correction factors. Now, based on these correction factors, then you can make sure you can correct the Douglas correlation to give a more accurate value of the more accurate compressor cost compared to the original estimation. Now you may ask me, or maybe this is just valid for nitrogen only. So how to check? You can check these correction factors by using other gases, other suction pressure, or maybe other condition, other temperatures, other condition as well. So if after you have done that, and then after you have applied a correction factors, maybe things would work out better, or maybe become more accurate. So yeah, I think that's pretty much it from me. I have nothing else to talk about. I think I'm gonna do another videos on the compressor because the author have two parts where he will design a multi-stage compressor, which I think is pretty good. Okay, that would be all from me. Thank you all for listening. If you like the videos, give it a thumbs up. Consider subscribing to my channels, and I will meet you again in the next video. Have a pleasant rest of your day.